Hi, this is a video presentation for our paper, A Permutation Representation of Covering Arrays, and this is joint work with my former student, Jiang. And the goal here is to minimize the expected amount of time or the number of tests that we have to run to find or detect a fault that is present within a given system. So covering arrays are in this field called interaction testing, where we have a bunch of components in some system that we don't really know the properties of necessarily, and we want to detect or find faults in that system. So we have a bunch of components here, and these can be any components you like in the system. And we are going to build a bunch of tests. And the property of covering arrays is that at most a certain size that you specify, all of the interactions of these components at most that certain size are all covered. So the naive representation of covering arrays when used in genetic algorithms is to use the entire array as the individual, and then you crossbreed the individuals that way. But that has more or less failed because the representation is so large. So what we want to do in this position paper is to put forth the idea that if we have a smaller representation, we can have a much more effective solution with genetic algorithms. So the representation here is a permutation of the tests. So instead of having the entire test suite being the whole representation, we're only storing the permutation of the rows here being the tests. And the advantage here is that not only is this smaller, but the operator for crossbreeding individuals is very natural here, because if you have two permutations, ordered crossover will allow you to do that. So the problem that we're trying to solve here is something called mean time to failure. There are other terms for this. So the mean time here is the average placement of interactions here. So if we put a lot of interactions at the beginning, then that will lower the average, the mean time to failure. And so this is the problem that we were able to solve, and we were able to reduce the MTTF value of many covering arrays as a result.
Okay, I think we're live. I'm just gonna wait till we're sure other people are saying, okay, I see claps, but can someone say in the chat if they can see our stream? Okay, Bobby says we're live. So we're live. Good. Thank you for I was commenting that I like the Blackboard style. So I guess my first question would be there you go. Myra is asking for a question. Can you give us an example of a permutation versus an array?
Yeah, sure. So an array is literally just a two-dimensional grid. So like a 2D array, and a permutation is just an ordering on, in this case, the rows. So we're interested in a representation of covering arrays that is useful for genetic algorithm purposes. And a permutation is a much smaller representation compared to the giant array, which is what most previous works have done. So yeah, so a permutation is just an ordering on the rows in this case, which is a lot smaller than the whole array.
So how does approach scale then? I guess you can have, I don't know, hundreds of, like a vector that's 1,000 lines long. So I guess, yeah, basically if you comment on scalability.
So the mathematical definition allows you to have any number of columns that you want. So in fact, it could be trillions of columns long if you wanted to. But in a realistic setting, it's applied to an actual system. So the columns are representing the components of that system. So depending on how fine-grained you want this to be, so if I have 10 components versus 1,000, it really depends. And as the number of components increases, the number of tests to adequately test the system also increases, but only in a logarithmic way. which is pretty cool. So what we want, instead of having something times something be the size of the representation, we only have one of the dimensions be the representation, which is a lot smaller. The time to evaluate the fitness function is exactly the same, pretty much. But the representation is a lot smaller, and it allows us to get further improvements because the search space is so much smaller.
Thank you. Another question. Well, more comments I want to read from Myra. Permutation arrays have been used as seeds for covering arrays. Seems like there is a connection here. I guess you can seeding as well.
Yeah, I see that question. So permutation arrays, even though it sounds exactly the same, it has only a slight relation in between. So permutation arrays are basically just, in a different sense, a more compact representation. But if we use genetic algorithms toward that particular type of array, which I've done in a personal project, the size of the dimension is very similar. It's something times something else. Whereas if we just have a simple array like this, then you can always apply a permutation to it regardless of the contents or how it's evaluated. As long as it has the same type of structure as a covering array does, we can always have this permutation type representation. But I do see that question, and I do think it's worth exploring applying this to other types of arrays like permutation arrays. There's a more complicated name to them. There are different types of things which are more related to a genetic improvement type setting in terms of trying to do fault localization onto what paths through the code are the ones to search for, and also to have automatic software repair actually be automatic versus having someone design the test suite for you, and to have this thing not only generate the test suite for you, have no humans involved at all, but have to have guarantees that the human may or may not have thought of when designing the test suite. So yes, it could be applied to many different types of arrays.
Cool. Slightly different question. In program repair or GI, there was a switch from full verbose abstract syntax trees to a patch or delta representation. Do you see this move from full arrays to permutations as similar?
I don't think so, because it's just similar in the sense that it's a different type of representation, but the sentiment behind that switch from patch to delta isn't quite the same as this, because it's still doing the same fitness evaluation, like literally exactly the same, but applied the fitness to different parts of the test suite at different points. So it's still going to evaluate the same number in some sense, in terms of the array actually being a covering array, but the value that we're calculating is different. So whereas with patch and delta, that's a totally different viewpoint on how to actually evaluate whether a program actually passes a test suite.
Okay. There aren't any more questions. Wes did comment that he liked your Blackboard style. I do want to say, sorry, still a few seconds of the of this talk, just to say that this is the last talk of the day, and we'll have a best presentation award. So right after this Q&A, I'm going to post a link so that people can vote. You have one vote; it's anonymous, and as I say, we have one vote. So. I will post a link so you can vote anonymously, and during the awards session, we will reveal the winner of that. So please vote during the break. And one last, I guess, sorry, we've got 10 seconds. I'm still under pressure which question to ask. I think I'm gonna give up, sorry. We're going to go into this discussion session in a sec.